Welcome back, Physics 30. This is the CO1.4 section of the conservation unit. So in CO1.3 we looked at kinetic energy. Now we'll look at potential energy. So define and calculate the gravitational potential energy of an object and solve problems involving gravitational potential energy. So we've just discussed how an object is said to have energy due to its motion. So that was kinetic energy. The word kinetic implies moving. So that's kinetic energy. It's also possible to have potential energy. And of course, potential, first of all, here we'll write down moving. And potential is stored energy versus moving energy. So it's energy associated with forces that depend upon, so now it's stored because it depends on its position or configuration. So like a stretched elastic band, the configuration of that implies that there's stored energy. Or something lifted off the ground, it's stored because if you let it go, it falls down to the ground. So yeah, in physics here, we're talking about the positional part of it. So various types of potential energy can be identified, the spring of a wind-up toy, etc., just like I mentioned. But here we're going to be looking at gravitational potential energy. So energy, something stored due to being off the ground, held above the ground, and having that stored energy. So due to its position relative to Earth. So a raised brick has the ability to do work because when it's released, it will fall due to the gravitational force that's being pulled on it, and it can do work into driving something into a ground. For an object of mass m to be lifted vertically, at least equal to its weight, and of course, if we did that, it would be lifted up at constant velocity, work must be done by a person's hand. To lift the object without acceleration, we would have this, right? So we'd have, if you take a look here, we have Fg pulling down, F exerted by hand pulling up. So these would be equal and opposite, giving a vertical F net equals 0. So that's where the constant velocity would come into play. Okay, so without acceleration, here we can have that. I'll just show that. So we're lifting up with an equal and opposite force to Fg to a height h above the ground. The person does work equal to that external force. So just like before, we had work is equal to change in energy. But in this case, the energy is potential energy. So the work done we lift in lifting it is equal to the potential energy gained. And of course, EP is equal to mgh. So EP is gravitational potential energy measured in joules again. M is mass of the object. G, of course, is 9.8 meters per second squared, and H is height. Now notice here I put in the positive 9.8 because since we know vertically F net is equal to what do I call it F external plus Fg. F external plus Fg, so if I minus Fg minus Fg, the force that I need to apply is equal to the opposite Fg. Okay, now you could think of it as Fg is equal to mg. Okay, and whatever I have is my mass, I have my gravity, of course, negative 9.8. It's kind of off the screen. But if I take the negative of the negative there, it becomes 9.8. So that's why I use this. So opposite to negative 9.8. So I can calculate it directly without having to do this every time because I know that it's equal and opposite to Fg. So I could just simply use positive 9.8 because that's what I'm lifting up with. So So we can say that work done on lifting an object has been stored as gravitational potential energy. The work done on the object is equal to the energy gained by the object. The work energy principle can be thought of as a change in potential energy. So this is what I had on the previous page there. And of course, just like kinetic energy, I could have started out by saying, okay, W is equal to the change in potential energy, which is EP final minus EP initial, where here I use number 2 for final, number 1 for initial. It doesn't really matter which way you do it. Gravitational potential energy depends upon the vertical height of an object at some reference level. So it doesn't have to be always lifted from ground. It could be lifted from some area above the ground. And then comparing that, the gravitational potential energy of a book held high above a table, for example, depends on whether we measured h from the top of the table, the floor, or some other reference point. The important part is we're looking at the change in potential energy, so in between which levels. So you have to choose a reference point and then calculate the change between the two areas. Okay? An important result we discussed earlier concerns the gravity force, which does work only in the vertical direction. So lifting something up or dropping it. The work done by gravity depends only on the vertical height and not on the path taken. I should likely highlight that too. So from initial to final and not necessarily on the path that was taken there. And we'll see that in this example here at the bottom. So potential energy changes during a roller coaster. A 1,000 kg roller coaster moves from point 1 to point 2, then to point 3. What's the gravitational potential energy at points 2 and 3 relative to point 1? So part A, we're going to go from here to here. And then for the second part, we're going from here to here. And then what is the change in potential energy when we go from 2 to 3? And then repeat, but look at point 3 as a reference point. Okay, so we'll do that on the next page. I left some room there for us to do that. Okay, so we'll do the first part here. So part A, going from 1 to 2 and then 1 to 3. So I can write that like this. Position 1 to position 2. And then position 1 to position 3. Now you can technically we're figuring out the change in potential energy, but what we can do is for H here, figure out the change in height. And of course that's what we're given here. We're given the change of height in between position 1 and position 2. It's 10 meters. So this was 1,000 kgs. And again here, use positive version of G. So since we're lifting up against G, assuming constant velocity, we're using the positive version because we're lifting up, just like I said before. So we don't have to do this rationale over and over and over again, like you could, but then realize that, oh, I'm lifting up against gravity, so opposite of negative 9.8, positive 9.8. That's a key thing you can do every time. So here we get 98,000 joules. Then going from position 1 to 3, so from 1 to 3, we're going here, then going down 15 technically. So 1,000 kgs. Again, use 9.8 because we're lifting up, even though we're going down here. We're always assuming that when we're lifting something up, it's positive, but the height is negative, so it's kind of awkward. The signs are a little bit awkward for that. Round that off to 2 sig figs. We use that. So again, over here, always use positive 9.8. Even if we're going down, that going down part will be applied here. Okay, so always use a positive 9.8 for little g here because we're assuming we're always lifting up against gravity, so it's positive. For part B, we're going from position 2 to 3. So from 2 to 3, start, finish. So you can see 10 and 15, it's going to be 25 in the downwards direction though. So position 2 to position 3. So 1.0 times 10 to the 3. Again, 9.8 to the positive, and moving down negative 25. It's going to give us negative 255,000. Round that off to 2 sig figs. Negative 250,000. And then last one, for part C, it says repeat number 1. So number 1, we went from 1 to 2 and 1 to 3. But this time we are using reference position 3 as my starting point. So it's going from here to here, here to here. You know that last one's going to be kind of funky. So we're going from position 3 to position 2. And then the last one, yeah, it's funky because we're going from position 3 to position 3. Okay, so what we moved here from position 3 to position 2, from here to here, so it's 15 plus 10 in the positive direction. So that's going to give us 245,000, but run it off to 2 sig figs. That. And then position 3, yes, for moving from one point to the same exact point. So yes, it's kind of cheesy in that the height is going to be simply 0. We're not moving it at all because it's staying at the same point. Good. So here we have no energy movement. Here we have gain in EP. Here we have loss in EP. So a negative, even though we're moving it down, the negative doesn't mean direction. It just simply means gaining energy or losing energy. And in this case, we lost. Here we lost. Loss in EP, gain in EP. All right, so that's all there is to it. You should be able to do the CO 1.4 assignment. We'll see you again.